Hello, AP Statistics. Welcome. We're going to do our chapter 5 multiple choice practice right now. Here we go. All right, so our first one, we're looking at the probability of being ticketed if you haven't been ticketed and on the 10th day you think you're going to get ticketed. Now, the deal with this one is that because these probabilities are independent, it doesn't matter what the previous probabilities were. The next probability is always going to be the same. So we choose. So we choose 1/3. All right, and I'm going to be moving through this a little bit quickly. I was not able to record this video during class, but still going to be great. So with this one, if you go ahead and read it, the issue that's going on with this one is we want to decide which one of these is an accurate probability model. Now, the two things that we're looking for when we're trying to decide if something is a legitimate or a legitimate probability model is that each of the probabilities are between 0 and 1 or from 0 to 1, and that all the probabilities add to 1. So obviously we've got this -1, so this one's out. It turns out that this sum for D is definitely greater than 1. This has probabilities 4, 5, 3, 2, so that's not legitimate. And 1/4 times 5 is greater than 1. And you'll see that if you add these, the sum is definitely going to be 1. All of these probabilities in here are from 0 to 1, and so we choose C. Moving on, we've got a two-way table. We want to know what the probability that the student typically takes a bus to school. So if we're looking at everybody that took a bus to school, of those people, there were 170 that took a bus out of 550. So you calculate 170 out of 550. And whatever that works out to is the answer. I guess I could get my calculator. And after putting that in the calculator, I get that this is approximately 0.309. I swear that's a 9. Which is B. Awesome. Okay. Moving right along to to the next one. All right, so now we're looking at the same two-way table. We want to know the probability that if they say there's a junior, what's the probability they walk to school? So what we're looking for is the probability that they walk given junior. And remember, when we're looking at two-way tables, this thing that we're talking about, the given part, that's all we're looking at. So we're only concerned with juniors. And the people that walk that are juniors are that 48 out of the total of juniors, which is 300. I throw that in the handy-dandy calculator, and I get approximately, what did I write? 330, 48 divided by 300. I get 0.16. And so we choose B. All right, and for the next one, we've got the same two-way table. And we want to know which following statements is true. So first of all, I'm going to decide, are these two events mutually exclusive, right? If they are mutually exclusive, then there are no things in my group of events that are both walking to school and juniors. And that is not true because there are these 48 juniors that walk to school, so they are not mutually exclusive. They have 48 events that they share in common. And so I'm going to go ahead and eliminate the things that say that they are mutually exclusive. So A says they're mutually exclusive, C says they're mutually exclusive, and we know that they're not mutually exclusive, so E is out. So now we need to determine if these two events are independent. If these two events are independent, then it should be the case that the probability of walks given junior should be equal to the probability that they walk. And if you calculate that probability, it is indeed true. So this statement is true. You can put in some numbers and find that it's true. Because that statement is true upon calculations, then we can say that those two events are indeed independent, and we choose B. All right, event A occurs with probability 0.2, event B occurs with probability if A and B are disjoint, if they're mutually exclusive, then, right, so that means if they're mutually exclusive, we're looking for probability A or B. It should be 1, right? Because if they're mutually exclusive, they don't share any events in common, right? So this particular one has a probability of 0.8. This particular one has a probability of 0.2. If either one or the other happens, then I'll just be adding these two probabilities, and thus I choose A. It's also nice to look at these answers and figure out that if this is the case, then there is no overlap. There is no such thing as probability A and B. So those are definitely out immediately. And then, yeah, that means that one's not true. And A or B, this is the product of the two. And we know that or means add. All right, so it says that probability A is 0.2, probability B 0.52. Says the two are independent. What is A or B? But it does not say that they are mutually exclusive. And we know that they are mutually exclusive because if we added them, they should add to 1 if they are mutually exclusive. So these two are definitely not mutually exclusive. So that means that we have to apply the rule that if they are not mutually exclusive, then the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. All right, and so if we calculate that, that's going to be 0.24 plus 0.52 minus 0.24 times 0.52. We'll go ahead and calculate that. And after I have performed that calculation, I get exactly 0.6352, which is C. All right. So people with typo negative are universal donors. So we've got this situation here. We want to know the probability that at least one of them is a universal donor. So first thing I need to consider is that the probability of at least one is going to be the complement of all right, so I'm going to go ahead and calculate. So first of all, I also need another complement, right? I need 1 minus the probability that they have type O. And I think that this is what it should say, none. Actually, sorry, probability none. 1 minus the probability of none. All right. So 1 minus the probability of type O, 1 minus probability, this probability is actually 0.072 or 0.928. All right. So, and the probability that none of them are type O donors, right? If we're doing 10, so the probability that none are universal donors or have O negative is going to be equal to this 0.928 to the 10th power, which is 0.474 approximately. So now going back here, we need to just take this complement. So 1 minus 0.474 turns out to be 0.526, and the answer C. All right. wow, that's a nice thing. We're talking about people that died. Fantastic. Um, and we're ignoring a smaller number. All right, diabetes caused 2.8. Okay. Good grief. Okay. So we got some people. We've got this situation where we have white and we have black and we have Asian, and the probability that they died and were white was 0.86. This is really strange. But here we go. We're making a tree diagram for this. All right. Among Caucasians, we have diabetes, and then we'll call this one not diabetes, and then we'll do the same thing for each of these categories. We'll go diabetes, not diabetes, and then here we'll go diabetes and not diabetes, and we're going to fill in these probabilities. So, okay, of 2.8%, so this is 0.028, which makes this 0.972. And then over here, sorry, that is a D, even though it looks strikingly like a P. All right, so among that subgroup, this is 0.044. Which makes this 0.93956. My eyes don't work very well. All right. Occasionally. And then over here, this is 0.035. And of course, I'm taking the complement in order to get the missing probability here. All right. So now we've got our tree set up. We can figure out the probability that chosen death was due to diabetes, right? So there are three ways that can happen, right? That can happen this way, and this way. So the probability of diabetes is going to be equal to 0.86 times 0.28 plus 0.12 times, I'm going to run out of room here, but that's going to be okay, 0.044 plus, and then the last case, 0.02 times 0.035. And we'll go ahead and take a moment to calculate that. Upon calculating, I find that this is approximately 0.30. Well, it's exactly 0.0130100. And so, the closest answer, because it says about, and it is definitely about 0.030. All right. In your top dresser drawer, you've got 6 blue socks, 10 gray socks, unpaired and mixed up. One dark morning, you pull 2 socks from the drawer without replacement. Let's see. What is the probability that 2 socks match? Okay, so that would be the probability. So probability blue and blue, or the other way that can happen is we're looking at the probability of black, or sorry, gray, and gray. All right, so that's the 2 ways that can happen. Only problem is that if we look at this, right, we gotta consider that when we pull one out, we're less 1, right? So this particular probability, blue and blue, the first time you do it, your probability is going to be 6 out of 16. The second time that you do it, it's going to be the probability of 5 out of 15, right? Because there's 1 less sock. And then if we look at the probability of a gray sock, we've got first 10 out of 16. And then the second time we pull one out, there's 1 less, so it's going to be 9 out of 15. let's go ahead and do some calculations. All right, so when you get this thing all worked out, you get a, actually it's exactly 0.5. And so we choose D. And that finishes it up. Thank you all so much for watching. I made this special for you guys. So have a good day. And if it's not a good one, I really hope that it gets better. Thank you.